Once again, we're back together, right? So this time we're looking at chemistry, the June exam for Gauteng. So please, if you haven't subscribed, do the right thing, guys. All right, and yeah, I think. Of course, if you are looking for assistance with maths and science, we've got our camp that's coming up, and please do join us there, right? All the details that you need to get in touch with us will be on the description of this video. Just follow the link tree link that is there. All right, so ladies and gents, without any further ado, let's start with the multiple choice section, right? So let's go. They say consider a condensed structural formula, right? We've got CH3, CH2, CH2, and OH. So in this case, we've got, this is definitely an alcohol. They say, what is the name of the functional group? So remember that the functional group of alcohols is the hydroxyl ion, okay? Or you say hydroxyl, however you want to pronounce it. Okay, I'll just make a color change of my pen, right? So the next one, they say consider the compound below. Which of the following is the IUPAC name for this compound? All right, so first of all, let's check, right? What's the longest chain that we can get from this guy? So let's see if we've got 1, 2, 3, 4, 5, 6, and 7. It seems like I cannot get any more than 7, so I'm just going to consider that to be my straight chain, okay, my parent chain. All right, and if I look from the right-hand side, my side chain started carbon number 2. From the left-hand side, they started carbon number 3. So we get a lower combination of numbers from the right. So I'm going to say that's carbon number 1, 2, 3, 4, 5, 6, and 7. Right, so now that means at carbon number 2, I've got a methyl group, and I've got another methyl group there. But you can see we've got another one at carbon number 4, right? So we've got 2,2,4 trimethyl, but we also have an ethyl at carbon number 5, right? So now note that E comes before M, right? Ethyl and methyl. So in this case, we're going to start with the methyl, with the ethyl. So this would be 5 ethyl, right? And 2,2,4 trimethyl, and this would be heptane. So the one that looks like the correct one is definitely C, okay? Right, please don't forget about that rule of alphabetical order. Right, so now the next one, they say we've got ethanol, ethanoic acid, and ethane are compounds that are found in a laboratory. Arrange the compounds mentioned above in decreasing order of vapor pressure. Now, so which means we start with the one that has the highest vapor pressure, right? And to the one that has the lowest vapor pressure. Now, guys, what I need you to remember is that vapor pressure, okay, is kind of inverse to the strength of intermolecular forces. So let's first arrange which one has got the strongest intermolecular force. In this case, it would definitely be ethanoic acid. So this would be the first one with the lowest, okay, vapor pressure. But let's talk about the strength in intermolecular forces. And then it would be followed by ethanol, right? And then it would be followed by, remember, both these, this has got hydrogen bonds, right? So, but it has two sides of hydrogen bonds. This one has got one side, ethanol has got one side. And then we've got dipole on ethanol, right? So that would be the next one. And of course, the last one on London forces is ethane, right? So now that means that in terms of a decreasing order of vapor pressure, right? So which means we're going to start with the one with the highest vapor pressure. And remember that the one with the highest vapor pressure is the one that has the lowest intermolecular force. I hope you can you get that, right? So highest vapor pressure means that we've got lowest intermolecular force, and that means it's going to be ethane, right? Okay, and then followed by ethanol, okay, and followed by ethanol, and finally it would be ethanoic acid. Okay, so where do we get that? So we said ethane, ethanol, ethanol, and ethanoic acid. So that would be B. That would be the one that we choose there, and that would be the decreasing order of vapor pressure. Okay, I hope that makes sense. Okay, all right. In fact, decreasing vapor pressure so means that we're going to start actually with the one with the highest vapor pressure. Yeah, actually that is quite correct. Okay, yeah. In fact, I'm confusing myself there. All right. So in this case, we are going to go to the next one. They say which of the following reaction types will be used to prepare ethene and propane from pentane under high pressure and under high temperature and pressure. So remember, in this case, what are we doing? We actually are taking a large molecule and we're breaking it down into smaller molecules, and definitely that would be cracking. However, because we're using high temperature and pressure, this is thermal cracking. Okay, so next one. 1.5 simply says the graph below represents the relationship between potential energy and the cost of the reaction for a chemical reaction, a certain chemical reaction. They say the heat of the reaction for the reverse reaction is. Now note, if we were to look at the forward reaction, right, the heat of the reaction would be the energy of the products, right, minus, so this would be the energy of the products, minus the energy of the reactants, right, the potential energy of the reactants. So you'd say 1 minus the minus 3, and so that would give you -2 for the forward reaction. So for the reverse reaction, it would be the other way around, right? So for the reverse reaction, you kind of look at your reactants as your products, right? So that would be in reverse, that would be 3 minus 1, so that would be 2 kilojoules. Okay, so there we go. All right, the next question. They say the equation below represents the decomposition of calcium carbonate. They say which of the following factors will not affect the initial rate of decomposition of calcium carbonate. So firstly, they say increasing the temperature, definitely that will affect the rate of the reaction. They say using powdered calcium carbonate, that will definitely have an effect. Adding a catalyst will have an effect. Increasing the mass of calcium carbonate, definitely that does not have an effect initially, but of course over time that might have an effect. So in this case, increasing the mass will not have an effect since that is a solid, okay? So that cannot be quantified in terms of concentration, right? The concentration of a solid remains constant. Okay, so the next one, they say the reaction represented by the equation below reaches equilibrium. So we've got that reaction there. They say delta H is greater than 0, so that's an endothermic, meaning the forward reaction is endothermic. They say which one of the following changes to the reaction mixture will change its color from pink to blue. So meaning we want to favor the forward reaction because that is what will cause the color change from pink to blue. So they say adding a catalyst. So remember, adding a catalyst will favor both the forward and the reverse reaction. Okay, place the reaction mixture in a container with cold water. So the forward reaction is endothermic. So In that case, it means increasing the temperature will actually favor the forward reaction since it is endothermic. So in that case, which means adding cold water would actually favor the reverse reaction. Okay, we don't want that. So they say add a few drops of concentrated hydrochloric acid to the mixture. Right, now notice hydrochloric acid, okay, contains, all right, so what it does is that it breaks down into these two. We've got the common ion effect in that it has the chloride ion in it. So definitely if we increase the concentration of our chloride ions, we will favor the forward reaction. And so that means it will turn from pink to blue. So definitely my answer there is C. Okay. And they say finally add water. Of course, that's not going to have an effect since we are looking at a liquid over there. Right, ladies and gents, let's go on to the next one. They say the following hypothetical reaction is at equilibrium at 500 Kelvin. Okay, so we've got A2 plus B, which will give us A and AB. Right, they say the diagram below shows the molecules involved in this chemical equilibrium at 500 Kelvin. Okay, so we can see that the white ones are A, the black ones are B. So in this case, what I notice is that the amount of AB, we've got 4 compounds there, or 4 molecules of AB, right? So we've got 4 molecules of AB. They say the temperature is decreased to 300 Kelvin. So now what they're saying to us is that we decrease temperature. Let's see what will happen to the amount of AB. So I see I had 4 initially. In fact, I had 5 even. But now the amount of AB has decreased. What does that tell you? That an increase in temperature must have then favored the reverse reaction, right? So that we now have a decrease in the amount of AB. So then what this tells you is that a decrease in temperature, remember that a decrease in temperature favors the exothermic reaction, right? So it tells you that the reverse reaction is exothermic. So it must tell us that the forward reaction is endothermic. Okay, right. Let's look at the options. They say which of the following statements is correct? They said the forward reaction is exothermic. Okay, that is not true. Right? Please remember, we said that in this case, the reverse reaction was exothermic since it was favored. So they say the concentration of AB is lower at lower temperature. That is not true. Remember that the amount of AB that we had decreased. Actually, that is true. The concentration of AB is lower at lower temperature. That is absolutely true. So that would be B there. They say the forward reaction is endothermic. But that is also true. The forward reaction is endothermic. Remember, we found out that the reverse reaction is exothermic, meaning the forward is endothermic. Well, that's weird. So that becomes an option as well. They say the concentration of B is higher at low temperature. Remember, when we lowered that temperature, what we did was to favor the reverse reaction. And so the amount of B the concentration of B would be higher. And you would see we had only one B there, and there are 3 of them at lower temperature. So it looks like we've got 3 options here. I'm not sure what the examiner was trying to do there, but nonetheless, it is what it is, guys. Probably they'd give you an answer if you chose any of those. The correct. They would actually mark it correct if you chose any of those options. Right. So the next one, they say, which of the following is the correct description for 10 moles per cubic decimeters of hydrochloric acid? So definitely that's a high concentration, right? And hydrochloric acid is a strong acid. Okay, so that's a concentrated strong acid. So D is the only option that's correct there. And then finally, they say consider the reaction represented by the following equation. They say which one of the following represents the oxidizing agent in the above reaction. Now remember, the oxidizing agent is the one that undergoes a reduction. And in this case, it means that you remember that reduction would actually be a reduction in the oxidation number. So Ag plus starts as 1 plus, it ends up as Ag0. So that definitely underwent reduction. So that means that Ag plus is our oxidizing agent. Okay, so it is A. Right, ladies and gents, that is how the multiple choice section goes on this question paper. It is quite an interesting multiple choice section. All right, let's go on to question 2. Hop on to question 2. So they say we've got a table below that represents 8 organic compounds. Okay, so quickly let's have a look at the questions that are given. Right, they say use the table above to answer the following questions. Right, they say to us define the term homologous series. So remember that when we talk about a homologous series, it's a series of organic compounds that can be described by the same general formula, right? Or in this case, we can say that it is a series of organic compounds in which one member differs from the next with a CH2 group. Okay, right, so any of those would work. Right, so they say consider the organic compound G. So that is G. So that looks like that is going to be butanol, right? C double bond O with an H there. They say write down the homologous series to which this compound belongs. Right, so that is definitely an aldehyde. So that is an aldehyde. Okay, and secondly, they say write down the condensed structural formula for this compound. Now note, in this case, what you can do is I can write it in the other way around. So that would be CH3, CH2, CH2, and CHO. So I can write it in this way: CH3, CH2, CH2, and CHO. Right, that's the condensed form of it. If you wanted to write it in the same order, I'd say CHO, CH2, CH2, CH3. I just prefer this order most of the time. Okay, so for that CHO at the end. And by the way, this can sometimes be a little bit disturbing. So perhaps it's better also to write it in that manner. But yeah, I think I would actually prefer the first one. Okay, right. So let's go on to the next question. They say write down the IUPAC name of the functional isomer of G. Now note that aldehydes and ketones are functional isomers of each other. So let's find a ketone there. Okay, and it must be a ketone with 4 carbons. Which one is it? So that would be penta. Okay, so no, that can't be pentan 1 own. Okay, so all right, so it looks like I've got methyl propanoate there. Are we still talking about compound G? Write down the IUPAC name of the functional isomer. Oh, so we're not finding it from the list there. All right, so the functional isomer, apologies about that. So the functional isomer of that guy would be, let's say that would be butane, butane 2-one. All right, so please note it would be a ketone that has a double bond, the double bond O sitting anywhere else except the terminal carbon. So whether it must be the two other carbons. So in that case, it means that it would be 2 either way, right? So that's butane 2-one. All right, so apologies about that. I thought they were saying it must be in that list. Okay, right. So the next question, they say, write down the IUPAC name of compound H. So if I look at there, okay, compound H. So firstly, let's look at what would be the longest carbon chain there. So it looks like it is 5 straight chains. Okay, so in this case, I've got methyl side chains, right, in carbon number 1 and carbon number 2 rather. Okay, so I've got a 2 there. But if I look at that, I also have bromides, okay? And the first one would be at carbon number 2 and the other one at carbon number 3, okay? Right, but now I see that I've got these side chains of mine there, okay? And notice, so where am I going to start numbering from, okay? Well, I'm going to actually start numbering from the left-hand side, okay? So I'm going to start numbering from my left-hand side and say, well, this is carbon number 1, that's 2, that's 3, 4, and 5. Okay, so, and by the way, the jury is still out on this. It still remains one of the arguing points. But in the CAPS curriculum, they actually choose the methyl in this case as the ones that would take precedence. Okay, so as a result, that's why I'm choosing that option. I know some of you may have referred to my video. Okay, and the IUPAC name, the IUPAC says something different, and in the CAPS curriculum, they seem to accept something different. But nonetheless, I will, for the sake of the marks, let's do what the CAPS curriculum says. Right, so this is going to be at carbon number 2. All right, so we've got 3,4. Firstly, dibromo. Okay, so that's dibromo. And we've got carbon number 2,2. All right, that's dimethyl. So that would be 2,2 dimethyl. Okay, and finally we've got pent there. So that would be pentane. Sorry, I can't fit all of that in one line. So that would be 3,4 dibromo, 2,2 dimethyl pentane. All right, so I hope that makes sense, ladies and gents. All right, let's go to the next portion. They say the general formula of the homologous series to which compound A belongs. All right, so if you look at compound A, let's go to compound A. So you've got C double bond O with an OH. So that definitely belongs to carboxylic acids. And that's what we wanted to find. But they said we must find the general formula. Right, so remember carboxylic acids, we can write it as CnH2nO2. Right, another way of writing that down is CnH2n plus 1, and you've got COOH. You can refer to my videos on organic chemistry, and you'll see that's exactly what we apply there. Right, on the next one, they say write down the letters of the compounds that represents. Right, so firstly, they say the positional isomer, of the positional isomers, rather. Okay. Okay, so let's see which ones represent. Okay, so they are not specific on which ones are positional isomers. Okay, so we need to find them. Okay, so firstly, I see we've got, remember that when we're looking at positional isomers, right, which is what they are interested in there, they must have the same homologous, they must be from the same homologous series, right? Okay, so let's see. Positional isomers, I've got butane 2 all there. Do I have anyone that is an alcohol? No. Well, yeah, that's not a positional isomer. So if I look at it, I've got pentane 2 on. Let's see, do we have another ketone there? Okay, let's see. I do have a ketone. This is definitely a ketone. Okay, it's got a C double bond O. And it's got 5 carbons. Yeah, it looks like it's C and D, right? So C and D are positional isomers. This would have, now note, this would have the double bond O at carbon number 3, right? So whereas the other one had at carbon number 2. So definitely C and D are positional isomers of each other. Okay, I don't suppose that there are any others. No. All right. Okay. Right, it looks like C and D is our only option. Right, and then they say the letter that represents an ester. Okay, so which one is our ester there? So definitely F is an ester. We don't have any other ester, so we've got F as the one there. Right, they say consider the organic compound B. So let's go to compound B. Okay. So we've got 2-methyl butane 2-ol. All right. Okay, so 2-methyl butane 2-ol. They say to us write down the structural formula. So please remember, ladies and gents, 2-methyl butane 2-ol. That means that I'm going to to start with the parent chain. So that's but. Okay. So at carbon number 2, I've got an ol, which is OH. But at carbon number 2, I also have a methyl, right? So I'd have CH3. I just don't have enough space there. Okay, so this is what it would look like. Carbon number 2, I'd have an OH, but I'd also have CH3 there. Okay, and please, you must insert all your hydrogens because otherwise the structure becomes incorrect. Okay, right, so this is what it would look like. Nothing wrong if you decided to put your hydrogen, your hydroxide rather, as OH like this. Okay, nothing absolutely incorrect with that. So that is correct. Right, now they want us to find out is compound B a primary, secondary, or a tertiary alcohol? Now note, the carbon that has the functional group has got 1, 2, and 3 carbons surrounding it. So it is definitely a tertiary alcohol. Right, and then finally, before we get to the last question, they say explain the answer to 2.5.2. Well, I've just said it just now, right? So there are 3 carbons that are bonded to the carbon atom, which has the hydroxide ion. Okay, right? So that is how you're going to explain that part. All right, now let's go on to the calculation. They say hydrocarbons are the principal constituents of petroleum and natural gas, right? A hydrocarbon consists of 81.82 carbon, 18.18 hydrogen, and they want us to calculate the empirical formula of this hydrocarbon. All right, now please, I want you to note, ladies and gents, so what I usually do, I'll just write that as a table. Okay, so I know it is a hydrocarbon, so that means we've got carbon, we've got hydrogen, right? So we first convert the percentages into mass, okay? So what I'm going to do there is that this represents 81.82 grams, okay? And 18.18 grams, right? Now, if I accept that that represents the mass, then we go to our periodic table. The molar mass of carbon, okay, is 12. And the molar mass of hydrogen, we know this is 1 if we check in our periodic table, right? So what I'm going to do is I'm going to use number of moles is mass divided by molar mass. So that's 81.82 divided by, for carbon, that is 12. And the same is true for hydrogen. So 18.18 divided by the molar mass, which is 1. All right, so let's calculate that. So we've got 81.82 divided by 12. Okay, that gives me 6.82. Okay, so I'm going to leave that as 6.82. And 18.18, that gives me 18.18. All right, so what I'm going to do, ladies and gents, what you do is you now divide by the smallest number, okay? So the smallest number between the two is definitely 6.82, right? So I'm going to divide by 6.82 on both. Remember, what I'm trying to do is to get a ratio. So 6.82. Okay, so let's do that. So that gives me 1. Okay. And for hydrogen, that's 18.18 divided by 6.82. That gives me 2.67. Okay. So that would be 2.67. Right. Now, remember, in this case, if you take it as 2.67 and you write it as a ratio, right? So remember, what happens now is that I can't have this, you can't have, a decimal as or even a fraction for your number of moles, right? So what we then need to do, if we express it as a ratio, so this is going to be 2 and 2 over 3, right? Or in this case now, that's 2 and 2 over 3. That's 2.67, right? But now, what can I do? Let's write it as a fraction. So that means that, remember, as a fraction, that's 3 times 2, which is 6. So that's 3 times 2, which is 6, plus 2, which gives me 8. So this is 8 over 3. Now, ladies and gents, to make that, it must not be a fraction, which means I need to multiply both by the LCD. So I multiply that by 3, but what I do on the one, I have to do on the other, right? So I'll have carbon, which is 3, and of course that cancels with that, and so hydrogen would be 8. So which means the empirical formula of my hydrocarbon should be C3H8. 8. All right, so that is how we are going to get to that answer. I hope that makes sense, ladies and gents. Right, we're going to move on to question 3. Go on to question number 3. So they say we've got a group of learners, right, that decide to conduct an investigation to compare the boiling points of the first 3 haloalkanes, namely chloromethane, chloroethane, and 1-chloropropane. Right, so remember that therefore becomes our independent variable, right? Okay, and then they say, and we're given the boiling points, okay, that becomes our dependent. Right, so firstly they say define the term boiling point. So please remember, by definition, the boiling point is the temperature at which the vapor pressure of a compound is equal to atmospheric pressure. Okay, right, so that is the definition. They say identify the independent variable, right? Remember, as I did say, what is our independent variable? That's the chain length, right? We can say that it is the chain length. Remember, they all have the same homologous, or they belong to the same homologous series. Okay, so the only difference is the chain length there. Okay, so we can say chain length. Nothing wrong if you said the molecular mass. Okay, each one has got a different molecular mass. All right, and of course you can also decide to use surface area. Okay, but I think chain length should suffice. Right, and the dependent variable in this case, remember, boiling point depends on the chain length. So that is our dependent variable. Right, so that would be our boiling point. And then they say the controlled variable. Now, what is it that we kept the same, right? The fact that they all come from the same homologous series, isn't it? Okay, so we can say the homologous series, or you can say the functional group. Okay, I think that would also suffice. Okay, and you can also even mention the type of intermolecular force, right? And nothing wrong with that. Right, so on the next one, we're going to say, so they say write down a suitable investigative question, right? Now remember, what an investigative question needs to do is that it needs to relate the independent variable to the dependent variable, right? So what we then do is, and it must be an open question, right? So meaning that you cannot answer the question with just a simple yes or no, right? So let's make an example. Let's say, what is the relationship, okay, of chain length versus the boiling point, okay? Or you can say, how does boiling point affect, or how is boiling point affected by the chain length? Okay, so in this case, please remember to have a question mark at the end. Okay, how is boiling point affected by the chain length, right? Or you can say the chain length of haloalkanes, all right, since we've got haloalkanes in this case. All right. All right, so the next question, they say to us, chloromethane is highly flammable. So they are giving us that statement. Okay, and they say, write down one precaution that should be taken when working with this substance in the laboratory. All right, so one thing that we know is that we must keep it away from open flames, right? Of course, because they've told us that it is flammable, all right? Or in this case, we must say that we must use a water bath, okay, in order to heat it. So that is the one precaution that we must always use. Right, so the next question, 3.5, they say which one of these substances, A, B, or C, has the lowest vapor pressure? Okay, give a reason for the answer. So please remember, we said the higher the strength of intermolecular force, the lower the vapor pressure. So they wanted to find out which one has got the lowest vapor pressure. Well, definitely it's going to be compound C, right? And they said we must give a reason. Okay, it has the highest, or it has the strongest intermolecular forces, the strongest intermolecular force. Or you can also mention the fact that it has the highest boiling point, right? Yeah, I think those would be acceptable. Right, let's go to the next one. They say the learners find 1-chlorobutane in the laboratory. Okay, how would the boiling point of 1-chlorobutane compare to that of 1-chloropropane? Definitely it would have a higher boiling point, isn't it? So they said, right, only higher than, lower than, or equal to. Definitely it would have a higher boiling point. They said, explain the answer to 3.6 by referring to the type of intermolecular force, right, the strength, and the energy. All right, so remember, they told us what we should actually give this in terms of, right? So we can say that an increase in chain length, right? Okay, so an increase or a higher chain length, okay, an increase in chain length will increase the strength. Notice we know that these are going to be London forces together with dipole will increase the strength. Okay, we can say that it increases the strength of our intermolecular forces. All right. Okay, so we know in this case they said we need to mention intermolecular forces, the strength. Okay, so we know that more energy is required. Note, ladies and gents, to separate, okay, the molecules. We are separating molecules and not breaking chains in that case. So we are separating, to separate the molecules of 1-chlorobutane. Okay, and so that's why it will have a high boiling point. All right, ladies and gents, so I will go on to the next question, which is 3.8. So they say to us, the learners decide to do another investigation with compounds J and K. All right, so there we go. We've got compound J and compound K. We've got butane, which is an alkane, and we've got 2-butene, all right, which is J there. Right, now they say bromine water is used to distinguish between compounds J and K by adding it to each compound in 2 separate test tubes. Right, they say the learners observe that one compound decolorizes the bromine water immediately, while the other substance only reacts after placing the test tube in direct sunlight. Okay, so they said write down the letter J or K of the compound that will immediately decolorize bromine water. So please remember that in this case, unsaturated hydrocarbons will decolorize bromine water quickly. K, it's a spontaneous reaction, so that will definitely be J. They say the reason that the other substance only reacts when placed in direct sunlight. So, ladies and gents, please remember that when it comes to alkanes, in that case, they need to have energy that is added into it. Okay, so the sunlight actually supplies the activation energy that is required. Okay, so they said the reason why it reacts when placed in direct sunlight is that sunlight. Okay, so sunlight will provide the amount of energy required. Okay, or you can say the minimum energy required. Okay, which is what we call, do you remember what we call the minimum energy required? Right, that's activation energy, right? So the activation energy, okay, for the reaction to take place. Right, so I'm going to, you can finish that statement there, but that's the reason why we place it in direct sunlight. So the next one, they say the molecular formula of the organic product formed in the test tube containing compound J. Right, so remember, this is where we are going to use, in this case, so they said the molecular formula of the product. So we're going to actually have something that looks like this. So we're going to break that pi bond there, the second bond. Okay, so we still have these guys looking like that, and so which means bromide ions would actually go on to carbon number 2 and 3. So that's what the molecular formula would look like. Okay, and so at 3.8, actually, look at me writing the structural formula. So that would be C4. That would be C4. That would be H8, isn't it? And Br2. That's the molecular formula that we would have. All right, and finally, they say to us a balanced chemical equation when compound K undergoes complete combustion. Right, so we're going to take K, right, which is butane. So remember, so we're going to have butane C4H10 plus complete combustion, it reacts with oxygen. We're going to form carbon dioxide plus H2O. All right, but please remember we need to balance that reaction. So C4H10, I've got 4 carbons on this side, so that would give me 4 carbons. 10 hydrogens means that I'll multiply that by 5. But now for oxygen, I've got 4 times 2, which is 8. I've got 5 times 1, which is 5, and that gives me 13, right? So that means that this will be 13 over 2 times 2, which will give me 13. But remember, we cannot have a fraction as our coefficient, so we're going to multiply everything by 2. So that would be 2 times 1, which would be 2 there. 13 over 2 times 2 gives me 13. 4 times 2 gives me 8, and 5 times 2 gives me 10. Right, so that is what we will have, ladies and gents, in terms of our balanced equation. Right, so we are going to leave it there for question 3. I hope that this was brilliantly answered. Okay, I hope that you understood. All right, let's go on to question 4. Question 4, right? We continue. They say the flow diagram below shows 3 organic reactions, namely reaction 1, 2, and 3. Various organic and inorganic products are formed as a result of these reactions. All right, so now we're going to answer the questions that follow. They say use the flow diagram above to answer the following questions. Right, so the first one, they say define the term saturated compounds. Remember that saturated compounds are compounds that consist of only single bonds between carbon atoms. Okay, right, and 4.2 says to us 2-bromopentane undergoes hydrolysis. Okay, so this is one of the reactions that occur there. That is in reaction 1. Where is reaction 1? Okay, there it is over there. Okay, so they say to us 2-bromopropane undergoes hydrolysis. They say to us name the type of reaction represented by reaction 1. Now, ladies and gents, I want you to please note that in that case, that would consist of a substitution reaction. Okay, so that would be a substitution reaction. Now, remember that in the place, now for reaction 1, right, so remember what would happen here. So which means that the halogen would come off and we would replace it with the hydroxide ion that comes from this a strong base, and so as a result that becomes a substitution reaction. So the next one says name the inorganic product that is formed in the reaction. So what would have happened? So remember, you removed the bromide ion, okay, and that means that the bromide ion that would have actually been part of the 2-bromopentane is removed, and you're replacing it with hydroxide ion, right? But now you still have the potassium plus that bromide that came off, and so that means that we are going to form, in that case, potassium bromide. Okay, they said the name, so I'm going to say this is potassium bromide. Okay, right, so that is our reaction. Now they say to us, give one condition, one reaction condition there, okay, that we are going to obviously react there with a dilute strong base, right? So it must be a dilute strong base that we use over there. Now remember that if we use a concentrated strong base, we are going to form an elimination reaction. Okay, so that's a dilute strong base there. Okay, right, I hope that you've got it, ladies and gents. All right, now let's go, and by the way, please, you can also mention that it happens in the presence of mild heat. So you can either mention that or the fact that there is mild heat. Let's go to the next question. They say, consider compound B. All right, so we'll look at compound B there. So we've now formed an alcohol, right? So this is going to be 2-pentanol, okay, or pentan-2-ol, right? So they say write down the IUPAC name. I've just given it that name there. So this is going to be pentan-2-ol. Okay, so that's our compound. And then they say, name the type of reaction represented by in reaction 2. Okay, so let's go and check reaction 2. So we are taking the alcohol, right, in the presence of heat as well as sulfuric acid. So we are going to form an elimination reaction there. Okay, and what would we then produce? Okay, so we would actually have, this is actually a dehydration reaction, right? So we're going to form an alkene there. They say name the type of reaction represented by reaction 2. So that would be an elimination reaction. And on the next one, they say write down the structural formula of the major product. Now, please, I want you to note, ladies and gents, whenever we are going to eliminate there, we're going to use Zaitsev's rule. And Zaitsev's rule simply says that if we are eliminating, we know definitely we're going to take away the hydroxide ion, right? But now which hydrogen are we going to take with it, right? So Zaitsev's rule says we eliminate the hydrogen that comes from the carbon with the least number or with the lesser number of hydrogens. So it would be this hydrogen that is eliminated. Okay, so that means I'm going to now form a double bond, right, between carbon number 2 and carbon number 3, right? And so that would be 2-pentanol. Okay, that is what I'd formed there. So they say to us, write down the structural formula of the major product. I don't have much space there. So what I'll do is I will try to write it over here. Okay, so we've got pent. So we know we've got a double bond between carbon number 2 and carbon number 3. Okay, so that is what it would look like. Okay, right, so make sure that the number of hydrogens, or rather the number of bonds around each carbon is 4. So we've got a hydrogen there as well as another hydrogen. Please note, it would be between carbon number 2 and carbon number 3 because we've applied Zaitsev's rule. Right, and then the next one, they say write down the chemical formula of the inorganic product formed. So remember, the inorganic product, we've eliminated H and OH, so we would actually form water, H2O, right? And that is the inorganic product. Okay, so the next one is reaction 3. They say in reaction 3, let's have a look at what reaction 3 looks like. So we're going to take that alkene that we have there, right? And remember, we said that alkene is 2-pentanol, and we are reacting it with hydrogen, right? That's hydrogenation. And of course, we're going to form an alkane, being pentane in that case. So we're going to break that pi bond over there and form pentane. Right, so firstly, they say, name the type of addition reaction. So we are reacting with hydrogen, so this is going to be hydrogenation. Okay, so that's the type of addition reaction that we have there. And they say give the chemical formula of the catalyst needed for this reaction. So remember, whenever you are hydrogenating, right, so we always use either platinum, okay, or we can use palladium, okay, or we can even use nickel as a catalyst. All right, so any of those. Platinum is more popular, so you can just mention that one. All right, now the next question, they say esterification is one of the most important reactions in both organic synthesis and the chemical industry. Okay, they say when making an ester, 60 grams of propan-1-ol reacts with excess ethanoic acid. Okay, so in this case, note that the ethanoic acid is in excess, meaning that the propan-1-ol, okay, propanol, in this case, propan-1-ol, would be the limiting reagent, right? So it would dictate or determine how much of the product is produced. And they say to us, and it produces 90.78 grams of an ester and water. Okay, right, now they say the balanced chemical equation below shows the reaction that takes place. So the first question that they ask us there is write down the structural formula for the ester produced. Okay, so note, what did we take? We took propan-1-ol, right? So it has 3 carbons. Okay, and we've got that oxygen that's in line with the carbons. Okay, and we took ethanoic acid, so we're going to have C with a double bond O. Okay, so everything else is just a hydrogen there. We're going to place those hydrogens, and that is the ester that we have. Okay, so that's what our ester looks like. Okay, please make sure that the number of hydrogens, right, does agree with the type of structure. And please note, in this case, that means that this is our functional group. Okay, that entire thing over there. You can encircle it, okay, just to show it there. Now they say to us, give the IUPAC name of the ester. So remember that you always name the alcohol side first. Okay, so the alcohol side is the one without the double bond O. Okay, so the alcohol was propan, so this is going to be propyl, okay, and ethanoate. Okay, please remember that the suffix for esters is oate. Okay, so that's propyl ethanoate. All right, now let's go to the next one. They say to us, give the chemical name of the catalyst used. All right, so they said the name and not the formula. So remember that anytime that we are undertaking esterification, we do use sulfuric acid as a catalyst. So that is sulfuric acid there. Right, and then finally they say calculate the percentage purity of propan 1-ol. All right, ladies and gents, so what you do for percentage purity, so it then suggests to us that not all of this propan 1-ol, right, not all the 60 grams were actually pure, right? So this is the total mass of the of propan 1-ol together with its impurities. However, we got the mass of the ester. Okay, so let's find out what is the number of moles of the ester that are formed. Okay, so number of moles of propyl ethanoate. This would be mass divided by the molar mass. Now, ladies and gents, we're going to have to use our periodic table in this case to calculate the molar mass. Now, the mass is 90.78 divided by, right, so the ester C5, so that would be 5 times 12. Remember that the molar mass for carbon is 12. So that's 10 hydrogens, so that would be plus 10 times 1. The molar mass for hydrogen is 1, plus this would be for oxygen, this is 16 times 2, so that would be the molar mass. Okay, so let's find out what the number of moles are. Okay, so we've got 90.78, that's divided by, that's 5 times 12, plus 10 times 1 plus 16 times 2. All right, so we get 0.89. That's the number of moles of the ester that are produced. And remember, the ester can only be made from the pure propanol, right? Propan 1-ol. So now let's find out. Our stoichiometric ratio says to us, for every 1 mole of propan 1-ol, I will get 1 mole of the ester. So meaning the number of moles of ester that I produce will be the same as the number of moles of the ethanol, the propanol that is used. So therefore it means that the number of moles of propanol, that's C3H8OH, will be equal to 0.89 moles. And please remember, why is that the case? Because for every 1 there is 1. So that's a 1-to-1 ratio. Right, so is it possible for us to get the mass of the propan 1-ol? Definitely, right? So we can say, well, we know number of moles is equals to mass divided by the molar mass. But because we're looking for the mass this time around, this would be number of moles multiplied by molar mass. Okay, we know that's 0.89. Okay, now note 3 carbons. So this would be 3 times 12 again, plus the molar mass of hydrogen. We've got 8 hydrogens. Actually, we've got 9, including the one from the OH. So I'm going to say rather 9 times 1 plus that 1 oxygen there. So that's plus 16. Okay, so let's get the mass of that guy. So this is multiplied by 3 times 12 plus 9. Okay, 9 times 1 plus 16. Okay, and I get 160.2. So that's 160.2 grams. So now we need to check the percentage purity, right? Okay, all right. So that's the ethanoic acid that we got there. Let me just check. I mean, we've got the 0.89 grams there. That's for the that's for the ester. Okay, and we now found out the mass of the ester. Okay, the mass of the ethanoic acid that we used. Oh yeah, I see where the problem is. I said C3, okay, where it was supposed to be, yeah, the the propan 1-ol rather, they gave us 60 grams over there. Okay, so that tells us that, yeah, I'm just wondering where is it that we went wrong on C3H7OH. Let me just check again, ladies and gents. So we've got C3, so that's 3 times 12 plus H7, okay, but I said H, so that's C3H8O, so that would be 9 hydrogens, and plus the oxygen, which is 16. Please, if you can verify for me, ladies and gents, that's the number that I get. So that's 3 times 12 plus 9 plus 16. Oh yeah, so I might have made a mistake. So the mass there is 54.29 grams. Okay, apologies about that. Right, now how do we calculate the percentage? So we're going to say the percentage purity, right, would be the mass of the pure or the reacted amount of propan 1-ol divided by the total mass, right? And this is multiplied by 100. Okay, so that's 54.29 over 60 times 100. And let's check what that gives us. This is divided by 60, and we multiply that by 100. Okay, and I get a percentage purity of 90.48%. All right, so that would be our percentage purity of, yeah, I think that's what I would get. All right, please just verify that for me as well. Okay, just to make sure that we get to the right answer. All right, so ladies and gents, we leave it there. All right, we are going to go on now to the next question. 5, they say a group of learners use the reaction between excess hydrochloric acid and magnesium ribbon to investigate one of the factors that influences the rate of a chemical reaction. They say the reaction that takes place is as is given there. Magnesium plus 2 hydrochloric acid gives us magnesium chloride plus hydrogen. They say the learners follow the method shown below to conduct the investigation at room temperature. So for experiment 1, they place a piece of magnesium ribbon in a conical flask and add 50 cubic centimeters of hydrochloric acid of known concentration. All right. So we would know the concentration of that magnesium, of that hydrochloric acid rather. They say simultaneously, they start the stopwatch and close the flask with rubber, with a rubber stopper containing the delivery tube. Okay, so we would measure the amount of hydrogen that's going in there. Okay, so they measure the volume of hydrogen formed in intervals of 20 seconds. Right, and then for method 2, or rather experiment 2, they repeat steps 1 to 3, but now they use 15 cubic centimeters, right, of the same hydrochloric acid diluted with 50 cubic centimeters of distilled water. So what are they actually doing? They are lowering the concentration of the hydrochloric acid, right? Okay, so of course that's going to lower the rate of the reaction. All right, so the first thing is they say define the term reaction rate. Remember, by definition, we say that it is the change in concentration of products formed per unit of time, okay, or you can say that it is the change in the concentration of reactants used per unit of time. Okay, and they say write down the conclusion of this investigation. Remember what I just said right now, that the lower the concentration, okay, the lower the concentration of hydrochloric acid, the lower the reaction rate. Okay, so we are showing the relationship between the dependent and the independent variable. Our independent variable right now would be the concentration of hydrochloric acid, and our dependent variable would be the rate of the reaction. All right, now for the next question, they say the concentration of of hydrochloric acid is 2 moles per cubic decimeters. Okay, so we want to find out. They say name 2 conditions that the learners had to keep the same to ensure that this is a fair test. Now, please remember, guys, to ensure that it's a fair test, everything else must be kept the same. So there must only be one independent variable. So concentration is the independent variable. So 2 other things that we need to keep the same is the temperature. Okay, temperature of the reaction. All right, number 2, the state of magnesium ribbons. Okay, or we can say the state of division. Okay, or you can say the amount of magnesium, right? So the state of division of magnesium ribbons. Okay, you can talk about also the amount of magnesium ribbons. Okay, so those are all the variables that we would keep the same. If you can think of one, please also you can include it in the comment section. All right, so the next question, they say to us, after completing the investigation, the learners represented the results obtained during each experiment, okay, on the graph below. So for experiment 1, you can see there that experiment 1 occurs at a faster reaction because we reached that completion much sooner than we did for experiment 2. Okay, so now let's find out what the next question is. They say give a reason why the same volume of hydrogen gas is formed in both experiments. Right, now what you need to remember, ladies and gents, is that In this case, you had the same amount of magnesium ribbon, right? It is the hydrochloric acid that was in excess, so meaning that the limiting reagent was the magnesium ribbon, right? So which means in this case, the reactions essentially would produce the same amount of hydrogen gas. Okay, so you can say that the magnesium was the limiting reagent, right, in both experiments. All right, so in this case, or you can simply just state that we had the same amount of magnesium ribbon there. Okay, so let's go on to the next question. Okay, so they say to us for 5.6, write down the volume of hydrogen gas formed during the first minute, okay, in experiment 1. Okay, so in the first minute, let's check there. Okay, so that's after 60 seconds. So in experiment 1, after 60 seconds, no, that's experiment 2. So the amount of hydrogen that would be formed, the volume would be 60 cubic centimeters. Okay, so experiment 1, that's 60 cubic centimeters. Right, and in experiment 2, let's check there, that would be the amount right there. So that looks like we've got 40. And remember, if I look at this, each step is increasing by 2. And how do I know that? That's actually increasing by 1. Okay, so in this case, this would be 41 and 42, right? And in this case, it means it would be 42 cubic centimeters. All right, so that's the amount of hydrogen that would be formed. Now they ask us the question, which one of the experiments, experiment 1 or 2, took place at a faster rate? Use the graph to explain. So please do note, it must have been experiment 1. Okay, so that's experiment 1. Right, and do note, they want us to explain why that is the case. Right, that we produced more hydrogen, right, in experiment 1 within the same amount of time, okay? So we saw that the amount of hydrogen that was made in 1 minute was much higher than the one that we made in the other one, okay? Right, now in the other experiment, we can explain that way, okay? So we want to now calculate, so that's 5.8. They say to us, calculate the average reaction rate, right, with respect to the magnesium in grams per second, right, in experiment 1, right, if the molar volume at room temperature is 24 cubic decimeters. Now, ladies and gents, please just follow this. So the rate of reaction must be in grams per second. So I need to find out the amount, the mass of magnesium, right, that was used within that amount of time. But now, remember, what do I have in experiment 1? I know how much of the gas I formed. That's in cubic decimeters, right? So I formed 60 cubic centimeters. So I'm going to say that number of moles of hydrogen would be the volume divided by the molar volume, So in this case, I've got the volume is 60 cubic centimeters, but I'm going to convert it to cubic decimeters because my molar volume is also in cubic decimeters. So I'm going to say divide by 60 divided by 1,000, right? So that would give me 0.06. Okay, 60 divided by 1,000 gives me 0.06. And now I'm going to divide that by 24. Okay, so let's find that out. So I'm going to have 0.06 divided by 24. Okay, so I get 0.0025. That's moles in this case. So that's the number of moles of hydrogen. But I'm looking for the mass of hydrogen, right? Sorry, not the mass of hydrogen, but the mass of magnesium that I would have used. Okay, so what I'm going to do now is look at my ratio between hydrogen and magnesium. So let's go back to our reaction. This says to me, apologies there, for every 1 mole of hydrogen, I would have used 1 mole of magnesium. So for every 1, there is 1. Okay, so that tells me that the amount of magnesium, therefore, would also be, so therefore it means the number of moles of magnesium would be equal to 0.0025 moles. And the reason for that is that because it is a 1-to-1 ratio. Right, now we're looking for the mass of magnesium, right? So I'm going to say, right, for the mass of magnesium, this is going to be number of moles multiplied by molar mass. So that's 0.025. Sorry, that's 0.0025. And the molar mass of magnesium, please note, okay, that is going to be, from the periodic table, we always know that to be 24, right? So we get, let's find that out. Okay, so our calculator is misbehaving. So we've got 0.0025 times, we've got 24 there. That gives us 0.06. So the mass of magnesium, this is the amount of magnesium that we lost. Okay, right. So now we want to calculate the rate of the reaction, right? So what does this mean? Okay, because I don't have sufficient space, I'm going to do it right at the bottom there. So I'm going to say the rate of my reaction is change in mass divided by the change in time. So notice in this case, my mass changed by 0.06. So I'm going to say 0.06. Okay, so 0.06. Okay, minus 0. In fact, perhaps I should say the other way around. 0 minus 0.006. So that's final minus initial. Remember, we used up all of the zinc, of the magnesium rather. So I ended up with nothing, but I started with 0.06. So this is divided by the time that it took was 60 seconds. Okay, that's in 1 minute. And in this case, I can already see how this is going to give us a rate of negative 0.001 grams per second. And the reason it is negative is because there is a loss in that mass. Okay, you don't necessarily need to put that negative there. Okay, so please make sure that your answer is positive. So rate must always be represented as a positive answer. Okay, so that is how we are going to calculate that there. And that's how we come to the end of question 5. I almost forgot question 5.3. I saw that when I watched this and I thought, sure, I don't want you guys to chastise me. So let's look at 5.3. They say the concentration of hydrochloric acid is hydrochloric acid solution rather is 2 moles per cubic decimeters, right? They said calculate the concentration used in experiment 2. Now remember, in experiment 2, what did we do? We had 15 cubic centimeters of the hydrochloric acid used in experiment 1, and we now diluted it by adding 50 cubic centimeters of distilled water, right? So that means what I'm going to do is use my C1V1. Okay, remember, every time we've got dilution, right, we're going to use this formula. So C1, that would be the first concentration. Remember, they said it was 2 cubic moles per cubic decimeters. Now I'm going to keep my volume in cubic centimeters. So initially, it was 15, okay? And there's nothing wrong if I keep it in cubic centimeters here, because my other volume is also in cubic centimeters. If you decide to convert it, okay, divide it by 1,000, but what you do on the left, you'll do also to the one on the right as well. Okay, so you'll see that concentration 2, which is what we're looking for. Now the volume, in this case, we added 50 cubic centimeters to the 15. So we now have 65. If you want to, you can divide by 1,000. But as I said, it's not really going to make a significant difference. So I'm just going to keep it as 65. And I'm going to keep this as 16. All right, so which means our new concentration now. Okay, so this will be 2 times, okay, so let's say 2 times 15, that's 30, divide by the 65. And so our concentration will be 0.46 moles per cubic decimeters. Okay, right, so that's how we'll get the new concentration of the hydrochloric acid solution. All right, please just note that. Apologies that I'd forgotten that. All right, so let's move on to the next question. Question 6 we go. They say the reaction between steam and chlorine gas reaches equilibrium in a closed container according to the following balanced equation. So there's our balanced equation, and we note there that delta H is greater than 0. It is positive. Okay, they say, is the reaction exothermic or endothermic? So remember, delta H greater than 0 means that the forward reaction is endothermic. Okay, and what this, they say, give a reason for the answer. Remember that the potential energy of the products must be greater than the reactants, or we can just simply say that delta H is positive, right? So that is the reason why. Now the next question, they say the graph below, not drawn to scale, shows how the products, the amount of products present in the container change with time at a specific temperature. The volume of the container is 5 cubic decimeters. Right, now notice in this case we've got hydrochloric acid that seems to be decreasing at a rapid pace, right? And the amount of oxygen is decreasing. Right, so if it is decreasing, hydrochloric acid is on the product side, then it's suggesting to us that we must then be favoring the reverse reaction, right? So they're asking which reaction is favored. Choose from forward or reverse and give a reason for your answer. So it is definitely going to be the reverse reaction. Okay, and they said give a reason because our products are decreasing, or the amount of products are decreasing. Okay, Right, so that is how we would answer that question there. Now they say, how do the rates of the forward reaction and reverse reaction compare at T3? Right, so this is when we still have the, if we look at T3 there, the graphs are actually parallel, or rather the amounts, or uh, definitely the graphs are parallel to each other. So this does suggest that we've reached a state of dynamic equilibrium. So we can say that they are equal. Okay. All right. So which means that the rate of the forward reaction is equal to the rate of the reverse reaction. All right. So let's go to the very next question. They say, oh, in fact, I didn't see that. They said write down only greater than, smaller than, or equal to, so it would definitely be equal to. Okay, right, and then the next question, they say, calculate the equilibrium constant for this reaction, right, at this temperature. If there was 5 grams of water and 5 grams of chlorine, right? So initially we had 5 grams of water and 5 grams of chlorine. Now, ladies and gents, I'm going to try and draw the table over here. Okay, let's try and fill in the table as much as we possibly can. All right, so first of all, I'm given my initial values, right? So, okay, let's just try and fill in that table as much as possible. So I've got initial, that's in moles. I've got change, that's also in moles. That's equilibrium, that's in moles, and that's equilibrium concentration, right? And that's in moles per cubic decimeters. Please don't forget to write down the SI units. Right, so I've got 2H2O, I've got 2Cl2, I've got 4HCl, and I've got O2 over there. Now, ladies and gents, let's check. So initially, I started with 5 grams of water and 5 grams of chlorine, right? So I would calculate the number of moles of H2O. That's mass divided by molar mass. So that would be 5 divided by, remember, water is H2O. So that would be 2 times 1, that's for hydrogen, plus oxygen, which is 16. So that would be 5 divided by 18. Okay, let's calculate. So that's 5 divided by, I get 0.28. Okay, so which means the initial moles of hydrogen, okay, would be of H2O rather, that's 0.28. And I'll do the same for chlorine. So the number of moles of chlorine, Cl2, would be mass, which is 5 grams, divided by, now remember chlorine is 35.5, but you've got Cl2, right? So remember you multiply by that number at the bottom there. So this would be 2 times 35.5. Okay. Right, so let's calculate that. So that's 5 divided by 2 times 35.5. I get 0.07. So the initial number of chlorine is 0.07. Now remember, initially, this suggests to us that we did not have any amount of hydrogen chloride, okay, as well as oxygen, right? This was what happened initially in the reaction, right? Now, what we're going to do there is I'm going to assume that the amount of hydrogen chloride and and oxygen rather, would be 0, Okay. In fact, no, actually, that's not true, because in our graph, sorry about that, our graph seems to suggest that we started with a known amount of hydrogen chloride, which was 1 mole of hydrogen chloride. Apologies there, so we can assume it to be 1. Okay. All right, so that would be 1 mole, but the amount of hydrogen of oxygen is 0.3, so I would have started there with 0.3 moles. Right, now the reaction occurred, or rather proceeded as it did, okay, and we do reach a certain amount of equilibrium. Now what I notice is that at equilibrium the amount of oxygen is 0.1. So this says to me, at equilibrium I ended up with 0.1. Now please, I want you to notice, ladies and gents, because we are favoring the reverse reaction, I am now going to, now note in this case, it means I'm going to produce reactants, okay? It means I am going to lose products. So I would have started with 0.3, right? And at the end, I've got 0.1. So how much did I lose of oxygen? That's 0.2, right? Now to get the values of the others, so what I'm going to do, I'm going to use my ratios, okay? So I'm going to say, right, so remember that we use the ratios here for the change in moles. In fact, let me just use a different color there. So I'm going to use my ratio. I'm going to say for every 1 mole of oxygen, I am going to have 4 of hydrochloric acid, right? So for every 1, there's 4. So for 0.2, what is 4 times that? That will be 0.8, okay? And again, I'll do the same for chlorine. For every 1, there's 2 times of chlorine. So for 0.2, twice of that would be 0.4. And the same is true for H2O. Twice of it will also be 0.4. Okay, so that is important, ladies and gents. Now let's fill in the rest of this table. Okay, so now we know we started with 1 mole of hydrogen chloride. We used 0.8. What do we have at the end? It would be 0.2. And now remember the reactants we produced, more of it. I started with 0.07. I produced 0.4, so what do I have at the end? It would be 0.47, and that's the same for H2O. I started with 0.28. I produced 0.4, and so at the end I've got 0.68. Okay, so please, I want you to note that. Okay, I'm trying to get this guy to work. 0.68. Right, now remember we were given the volume there. They said it is 5 cubic centimeters, decimeters. So to get the concentration, I am going to take the number of moles at equilibrium, 0.68, divide by 5. So I'm going to find each of them. 0.68 divide by 5. So that will be 0.136. For chlorine, 0.47 divide by 5. That gives me 0.094. For hydrogen chloride, I've got 0.2 divide by 5. I get 0.04. And for oxygen, right, I've got 0.1 divided by 5. That should give us 0.02. Okay, right, so what did they ask us to find there? They had said we must calculate the value of Kc. Now remember, in as much as we favored the reverse reaction, Kc still follows the reaction. It says hydrochloric acid is our product, so that's the concentration of our product, to the exponent 4. That's oxygen divided by our reactants, that's H2O squared multiplied by Cl2, and this is also going to be squared. Right, and all that's left for us to do, ladies and gents, is just to substitute. So that's 0.04 exponent 4, 0.02, okay, exponent 1 divided by 0.136, that's squared, and 0.094, that is also squared. And all that's left for us to do is to put in some calculator work. So I've got 0.04, that's yx4. Okay, I'm going to multiply that by 0.02. And at the bottom, I've got 0.136. That would be squared multiplied by 0.094, and that's also squared. Ladies and gents, I get a very small Kc value for obvious reasons. So I get 3.13 times 10 to the negative 4, right? And please remember that Kc does not have any units at this stage, right? So that is how we are going to answer that question. All right, so now let's go to the next part of this. Okay, so they say to us, the pressure is now increased. Okay, how will this change? And by the way, please remember, I added all of them in my Kc expression because they are all in gaseous form. Please don't forget that. If it is not a gas, we do not include it in the expression. Right, so they say the pressure is now increased, right? How will this change affect the value of the equilibrium constant? Now remember, ladies and gents, when I look at pressure, I need to always check how many moles of gases we have on either side. So we've got 2 here, got another 2, got 4 moles over there. And on the right-hand side, I've got 4 plus 1, which would be 5 moles. Right. And now we want to know what's going to happen to the amount there. So they say to us, we are now going to increase the pressure. Remember that an increase in pressure will favor the side with the least amount of moles, right? So in this case, actually, they said, how will this affect the value of the equilibrium constant? Remember that equilibrium constant would remain the same. The only thing that changes the equilibrium constant would be temperature. Okay, so in that case, I want you to please note that it would remain the same. They say, give a reason for the answer. Remember that it is only temperature that changes the Kc value. Okay, right. And then finally, they say the reaction is repeated with a catalyst. Okay, draw a potential energy graph diagram of this reaction and indicate the non-catalyzed reaction, which is B, and the catalyzed reaction on the same axis. Right, let's see where I can grapple for some space there. Okay, so let's try and draw it over there. Okay, now remember for reaction A, we are going to have, this is an endothermic reaction. You must remember, keep that in mind. Delta H was positive. So that tells us we're going to start with a lower value and end up with a higher value at the product's side. Please don't forget to also, so this would be graph, the non-catalyzed one is B. So this would be B. Now, what would be the graph that is catalyzed look like? It would be exactly the same, only, right, the peak would be somewhat lower. So this graph here would be graph A. Okay, and please don't forget to label your axes, right? So this would be potential energy. Okay, and in this case, this is against reaction coordinates, right? Or you can say the course of the reaction. I think that's the more popular one, course of reaction. Right, so those are the two graphs that you have. Please remember that the graph with a catalyst would always have a lower peak in that case. Ladies and gents, that brings us to the end of question 6. Let's go on to the next one. Question 7, they say sulfuric acid is a diprotic acid, right? Define the term acid according to the Arrhenius theory, or rather in terms of the Arrhenius theory, right? So remember, according to the Arrhenius theory, that an acid, right, is a substance that produces hydronium ions when it is dissolved in water. Okay, right, so that is the definition of an acid there. Okay, right. Or you can say that it produces hydronium ions in solution, whichever one would that would work, right? So they say give a reason why sulfuric acid is referred to as diprotic. Okay, so remember in this case that when it ionizes, rather, it produces 2 hydronium ions. Okay, or you can say that it forms 2 protons, right, when it dissolves in water. Okay, right, so that is why it is diprotic. All right, so the next question, they say the hydrogen carbonate ion acts as both an acid and a base. It reacts with water according to the following balanced equation. Right, now they say to us, write down one word for the underlined phrase. So a substance that acts as both an acid and a base, we call this an ampholyte. Okay, so that's an ampholyte. Now they say to us, copy the equation above and indicate the conjugate acid-base pairs, right? So, fortunately, I can actually have it right there. So remember, so this HCO3 becomes H2CO3 on the other side. So that does tell us that these are conjugate pairs of each other, right? But we're going to indicate, so which means HCO3 received a proton. So this guy must be the base, right? So that makes this an acid. Okay, and which other ones do we have? That's another pair. H2O started as H2O, and it becomes OH minus on the other side. So in this case, H2O must have acted as an acid in this case, and so OH minus therefore would become the conjugate base of it. All right, please just note there. Okay, so we've indicated the acid-base conjugate pairs. Of course, you would have rewritten that and wrote it in your answer book. Okay, right, now let's go to the next question. They say to us a laboratory assistant was asked to prepare 2,500 cubic centimeters solution of hydrochloric acid with a concentration of 0.25 moles per cubic decimeters. Right, now they say the laboratory assistant had a bottle of concentrated hydrochloric acid which had the following written on the label. Right, so the chemical, hydrochloric acid, the density, 1.2 grams per cubic centimeters, right? And in this case, they said percentage hydrochloric acid by mass of solution is 36 cubic centimeters. All right, now they said to us, calculate the mass of hydrochloric acid contained in 2,500 cubic centimeters of 0.25 moles per cubic decimeters. Right, ladies and gents, so we've got the volume, right? We've got the concentration. We are looking for the mass. All right, so that means we can use our C is equal to M, small m over molar mass times volume. Our concentration is 0.25. We want the mass. And please note, hydrogen chloride or hydrochloric acid, right? The molar mass of hydrogen on the periodic table is 1, and chlorine is 35.5. So that gives us 36.5 in terms of its molar mass, right? And the volume is given as 2,500. Remember, we need to divide by 1,000 to make that into cubic decimeters, right? So that will give us 2.5, okay? Right, now ladies and gents, all we do is to cross multiply m times 1. Okay, so let's find that answer there. So that's 0.25 times 36.5 times 2.5. And I get a mass of 22.81 grams. Okay, please confirm if you get to the same value. Right, but that is the value that I actually obtained in this case. Right. Of course, given, that answer, there's a 5 there. I'm actually going to keep it as 22.81. All right, now in this case, we've got 50 cubic centimeters of a 0.25 moles per cubic decimeters hydrochloric acid solution, right, is used to neutralize 20 cubic centimeters, right, of sodium carbonate. Right, we're given the reaction over there. They say calculate the concentration of the carbonate solution. Right, so remember we are going to use in this case our formula C1V1 over C2, actually not C1 but rather CAVA over CB VB, which is equal to Na over Nb. Now notice this is our acid here and this is our base. Right, so the concentration of the acid 0.25 times the volume of the acid is 50. The concentration of the base is what we're looking for. And we know we're given a volume of 20. All right, now number of moles of the acid, our coefficient is 2 there. And the number of moles of the base, our coefficient is 1 over there, right? So let's do some gymnastics. Okay, so we've got 20 times 2 times CB, that's 40 CB, which is equal to, in fact, we might as well just do that with one calculation. So 0.25 times 50, okay, times 1, okay, which is equal to that, and we are going to divide that by 40. And so this is simply going to give us 0.3125. Okay, so that still gives us 0.31 moles per cubic decimeters. Now, of course, some of you would say, yeah, but we should have converted that volume to cubic decimeters. You may do so, ladies and gents, but there is absolutely nothing wrong. We should be able to get the same answer even if we didn't convert, right? What you should note, though, is that if you decide to convert, you must convert both of them. If you decide not to convert, both of them must be in the same units, which is cubic centimeters. Okay, right. And in this case, okay, the last question. They say, name a suitable indicator that can be used in this titration and give a reason for the answer. Now, ladies and gents, we have to know our indicators. Okay, so what are we taking here? We're taking a strong acid, right? And we're taking a weak base, right? Remember, if it's not hydroxide, then it should be a weak base. So which means our salt that we are going to form on the other side. Okay, so this would actually form an acidic salt. Okay, but in this case, we've got sodium chloride on the other side. Okay, so I would actually take methyl orange, right? Now you'll notice when you take methyl orange that methyl orange actually usually you'd get the type of acid that it, or rather the type of indicator that it is in this case, because we've got a strong acid and a weak base, we therefore that would be suitable. Okay, so I'd say for 7.3.3 that would be methyl orange. Okay, and they said give a reason, because we've got a strong acid and a weak base. All right, so that is how the cookie crumbles, and that brings us to the end of question 7. A clean piece of copper is placed in a solution with silver nitrate. The balanced net ionic equation is, so it's given there. They say define oxidation in terms of electron transfer. Okay, so remember, what is oxidation? It is the loss of electrons. Okay, so that is the loss of electrons. Okay. Right, and they say to us, what type of reaction does copper undergo in this reaction? They say choose from oxidation or reduction. So if you look at copper, it starts with an oxidation number of 0 over there, right? And it becomes 2+. It tells you that it has lost electrons, so it does mean that that is oxidation, right? And they say explain the answer by referring to oxidation numbers. Okay, we can say that copper moves from an oxidation number of 0 to 2+. Okay, so copper moves from 0 to 2+. Okay, showing us that it has actually lost electrons. All right, so that is how we're going to answer that. Right, now let's go to the next one. Okay, they say sulfur dioxide gas, that is SO2, is bubbled into an acidified potassium solution of potassium permanganate, as shown in the diagram below. Okay, so there we go. We've got potassium permanganate. Okay, so they say it is observed that the solution turns purple to colorless due to the reduction, okay, of the permanganate ion, right, into the Mn2+ ion. Okay, they say during the reaction, sulfur dioxide is oxidized to sulfate ions. Okay, now they say determine the oxidation number of manganese in the permanganate ion. All right, so first of all, ladies and gents, that's KMNO4. I'm not sure why they wrote 2 minus there, because then it would suggest that it is K2 when it actually has, it is with potassium. But remember, the permanganate ion is MnO4 minus, right? So I want you to please note this very carefully. So we know that oxygen usually has an oxidation number of 2 minus, right? It is in period 6 of your periodic table, right? So that means in this case, if I take for the the potassium, or rather for the manganese rather, in this case, so if I say, well, it's going to be the oxidation of manganese plus the oxidation of 4 times my oxygens, right? 4 times my oxygens. And now note that it would form a -1. So you'd have this guy giving us -1 at the end, right? So what does that say to us? Okay, so it gives us -1. So that means if I take my permanganate ion, right, whatever the oxidation state of it is, plus 4 times, remember oxygen I said is -2, this would give me -1. So ladies and gents, to get the oxidation number, so 4 times -2 will give me -8. If I bring it to the other side, -1 plus 8 would give me +7. So the oxidation state of my manganese ion there would be 7 plus. Okay, so that is how the cookie crumbles, ladies and gents, and we come to the end of this. Okay, that was out of 150. Right, and ladies and gents, if you are still struggling with the maths and science, please note that our camp is coming up. That is between the 1st of July till the 5th of July. Please do join us there. If you want more details, you can go on to our website, www.mlungisinkosi.co.za, or you can even go on to our socials. Okay, that's _Mlungisi Nkosi on Instagram, or you can say Mlungisi_Nkosi_center on both Instagram as well as on TikTok. All right, but all the descriptions that you need will be on this video. I hope that you were able to enjoy that. I will see you guys again next time, and please don't forget to subscribe and like. I'll see you guys. Shop shop.